Well, thank you for that. Thank you for that introduction, Stephen, and thank you for the invite. I'm really excited to be here and talk about the work that we're doing. For a couple of reasons. One is that I just really like doing the kind of stuff that we do in this project, and I really get excited to talk about it. But also because I actually think what we do has a lot of lessons for the way we think about scientific computing, particularly in the age of AMSEC and other such services that are coming down the pipeline. So I don't know if anybody here has ever seen me give a talk, but I have this problem, which is that I really struggle to just give a talk and talk about the work that I'm doing. I really like to make sort of a broader point about like, what is it that we're doing and how does it relate to other stuff? So I'm going to try to do that. And hopefully that spurs some discussion at the end and we can talk about a few things. So as Stephen said, I'm an astrophysicist by training, but I came out of grad school realizing that I did not like and was not very good at doing astrophysics. And so the decision I made was, that I was much more interested in saying, how can I help astrophysicists actually do science at scale? And spend most of my time solving interesting computational problems and then sort of wrapping that up in a nice little domain specific abstraction layer that our users can look at and actually do real science with. And so that's kind of what we're going to talk about. That's what this project is really about. So I actually want to start with a brief, I just told a story, but I'm going to tell another one real quick that's going to kind of ground the way I think about this problem. So this actually doesn't involve cosmology. So I have a friend in the same division that I work in, the high energy physics division at Argonne, who is not a cosmologist and is not a computational person at all. And she calls me up occasionally when she needs to do computational stuff and says, hey, can you help me with such and such thing? I need help, doing this and I don't really know how. I'm getting started on one of the machines. Can you help me out? And recently she came to me and she had this model that had been sent to her as a container image and she wanted to train it. And she had gotten a reservation or some nodes on one of our GPU systems here at Argonne, and she had requested 10 nodes and ran the thing, and it took 4 or 5 hours to run. And the only thing that she expressed to me at the time was, well, I need it to run in an hour. I don't know exactly what her science use case was that she needed to run in an hour, but she needed to run it in an hour. And so she was asking me for help making that happen. I diagnosed very quickly what the problem was, which is that she didn't know what MPI was and she wasn't using MPI. And so she was launching this job thinking she was launching it across 10 nodes, well, actually only launching it across one node. And sure enough, the logs, which she didn't know where they were or how to look at them, showed only output from 4 GPUs, which is the amount of GPUs on one node. And so the question that I want to ask, and I think this is a pretty common experience for people who are computing-oriented people who work a lot with domain scientists. And so the question I want to ask is like, what is the response? How should we be thinking about this problem and how should we be attacking it? And I'm not going to give an answer right away. I'm going to kind of wait till the end for that. But it's something that I think about a lot and maybe you can think about it too and we can have a conversation about it at the end. So before we get to that, I want to share what we actually do at Argonne and the science, because even though I'm not super science oriented, what we do is really amazing. So we are cosmologists. We're interested in the formation of the universe and really its growth and over long periods of time. So this is a video from one of our recent simulations. This is a state-of-the-art, like extreme scale, like literally flagship class cosmological simulation, where we're actually watching the evolution of the universe over billions of years, right? And to first order, what happens as the universe grows and expands is, in the early times, the dominant force is gravity. And the dominant source of this gravity is dark matter, which is this invisible matter that we don't see that causes structure to form in the universe. This dark matter collapses into these things called halos, and these halos then attract gas and dust and so forth and form stars and all of the things that we see in the universe today. These halos form into galaxies, these galaxies grow, and eventually you get kind of the universe that we see today. And this simulation that we're running is an appreciable size of the the box of the simulation is an appreciable fraction of the size of the observable universe. So this is a single rank's worth of data over the entire simulation. The entire simulation ran around a week on Frontier, 9,000 nodes on Frontier. So this is a big piece of software and a lot of compute and a lot of data. We write about 100 petabytes of data over the course of the simulation. A lot of that is checkpointing information, but nonetheless, even what we have at the end is very significant. And so then the question is like, how do you do science with this if you're not a science-oriented person, right? This is a huge volume of data. If you're a science-oriented person who's not a supercomputing-oriented person, this leads to a problem. And this is a problem that I think if you're a workflow person, you probably understand why this is a problem intuitively, which is we have petabytes of data across several different machines, right? So this is one simulation. We've run many. We're running more all the time. They're on several different machines, including Frontier, machines at Argonne, and machines and stuff on Perlmutter at NERSC. It's on several different machines, and it's in a custom format. And we want people to be able to do science with it without having to deal with these details. And so the first goal of the project is really, let's just provide a unified user-friendly interface to access and query this cosmological data while keeping the user, what I like to say, out of HPC space, right? Now, of course, we can't always keep people out of HPC space, right? If you want to do stuff at scale, you have to do HPC stuff, but maybe we can help them get started in a way that doesn't require them to spend a ton of time on the machines. And this is something that we actually have built and is actually being used by scientists. So this is a sort of a short video of a kind of workflow that a user would go through. And what they have here is a sort of domain-specific front end that allows them to ask questions of the data in terms that they're familiar with. So they're not writing any SQL. They're not doing any they're not like looking at raw columns. They're just saying, hey, you know what? I'm interested in galaxies above 100 billion solar masses, something like that. They write that. They press the button and then they wait. And hopefully they don't wait very long. This particular query runs in, I think, maybe 2 minutes, assuming that we get through the queue on time. But the point is they now have this data that they didn't even have to think about how to get it, that they were able to ask questions in sort of in a domain-specific way. And then they have these plots, and plots are nice, but they actually want to read the data and do something interesting with it. And so now they can download data, but now you have a problem, which is I'm providing you this data. It's in a format that you're maybe not familiar with, and there's actually multiple catalogs in here. So I talked about dark matter halos and I talked about galaxies. So this user has now a catalog of dark matter halos and a catalog of galaxies, and maybe they're interested in something that says like, hey, which galaxies are part of which dark matter halo? And so what we then do is we then provide them a data management or an analysis tooling that actually deals with all that information for them. And so you can see they were able to produce this plot, which involves a lot of complex relationships between the data with very little code, right? And so to a first order, this is a better way, and we believe, to build an analysis, right? You're not logging onto the machine, working on this custom format, having to learn how to launch MPI jobs. You're just kind of asking questions in terms that you're familiar with, and using software that understands your needs in order to do science. But I want to ask a question now. So this is the life cycle of one of these requests. User comes to us on the portal and they press the button, they put in their numbers and they press the button. And we basically use Globus front to back to manage and orchestrate this workflow. We have to figure out which machine it needs to go to. We send it to the machine. We do the computation. It gets submitted to a queue. It takes however long. It gets written to the file system, and then the user can then download it and do additional stuff with it, move it via Globus, all that stuff. And the question I want to ask about this is there anything special about this? And if you are the kind of person who shows up to a workflow community talk, my guess is you recognize there really is nothing special about this workflow from like a pure computational standpoint. It's like user comes in, we find where the data is for them, we manage the life cycle of the job of the workflow for them, and then we turn the data to them so that they can do additional work. What makes this special is really, again, not the core workflow orchestration that we're doing here. It's actually the domain-specific stuff that we layer on top of that. And what's really exciting is that at every point in this system, we have an integrated data management tooling that uses all the same language. So when the user is working on their machine, they're using this library that we've built that understands the relationships between the data. But at its core is just a data querying library with some nice domain-specific stuff on top. When users are working on the back end, or when the back end's doing a query, it's using the same domain-specific querying library to perform the query, making it very easy for us to write new queries for the users. And since, as Stephen mentioned, agentic tools are a big deal, the exact same thing is happening with the agent, right? When the agent, we have agentic tools that are using our backend in order to do interesting work, and it's the exact same thing. They query the data in using this common tooling. It comes to them in a particular format that they can then open with the common tooling and then do additional work. Okay, so domain-specific stuff is cool, and like I'm a computational person who works with astrophysicists, and so I do a lot of astrophysics tooling. But again, I want to go back to this question, which is how special are the problems that we're solving? And I think the answer is a lot of times not the super special. So I want to revisit the challenge that we're working on and look at it in a slightly different light, which is to say, what we're doing here is really petabytes of tabular data on several different machines. And we need to support analytics-oriented queries, right? So now we've sort of taken the astrophysics out of it entirely, and we're just kind of looking at it from a data management and querying perspective. And again, when we look at it this way, it really doesn't look all that unique. And our real goal here then is what we think of as what we're doing is we're trying to build easy-to-use infrastructure tools that can be used across many domains of science. I think I have the same slide twice here accidentally. And if you zoom out even a little bit farther, we use tabular data. Not everybody uses tabular data. You might say, well, what we really have here is petabytes of mixed data, and we have this entire HPC system and these complicated workflows. And so the way that we conceive of what we're doing and the way that we try to make a connection to the larger community is we really believe that what we're doing here is building a layer of abstraction on top of traditional HPC to allow scientists to focus on what they do best, right? That's how we think about the problem. And so where we're at this point is, for now, what a user can do, they can do automatic querying across the full data set at scale. They have this great web front end that they can use to do these interactions, and they can have this common data format and analysis tooling. But we want to go further because with what we have today, you really can only do small scale stuff. You can do prototype stuff, and the data tooling works on the back end, but you still have to log into the machine and do all this extra work in order to, if you want to run across the entire simulation. And so tomorrow, and this is the metaphorical tomorrow, not the literal tomorrow, we're talking, we want to move from canned queries to automated analysis at scale. And we believe we have the framework we need to do that. Almost. And this is where it really gets into, so we are, I am part of Infrastructure Partners for AMSEC, and I kind of have this little spiel that I give every time anybody talks to us about AMSEC, because the problems of building the stuff on the right-hand side really doesn't have a lot to do with our ability to manage our own data or our ability to write code that understands the data and understands the way that the users use the data. The challenge is really more about orchestration of this stuff at large scale. So if you're running a single workflow, apologize. Somebody asked what AMSEC is. So American Science Cloud, which is this new initiative coming out of the DOE to build sort of integrated, sort of cloud-like infrastructure across all the DOE facilities. AMSC, usually pronounced AMSEC, so I apologize for using the jargon. So AMSEC's going to kind of fill some of these gaps. So the tricky part is that while running single workflows is very straightforward for us, the management of workflows at scales across several HPC-oriented facilities is a much more challenging issue, right? So I'm telling you that I'm envisioning this future where somebody can come to me and say, here is the code that I want to run, and I want to run it across your entire simulation. And I say, great, I will wrap it up for you. I will send it to the machine. I will run it. I will collect the results, and I will bring them back to you, right? And that sounds great in theory. But the challenge is not, again, the technical, how do we manage the data? The challenge is how do we actually manage the life cycle of all these requests and actually be able to do this in a systematic way? And there's a few real challenges that we face, which are, if you're a domain scientist, not interesting challenges at all. Things like logging, things like automated deployments and CI/CD, things like automated testing and security. So yes, I am advocating that we have a user who provides code that we wrap up and run on the system. And there are all sorts of reasons why that presents all sorts of security challenges. In the short term, that probably looks like users only allowing users who already have facility accounts to be able to access these kind of capabilities. But long term, I would hope we're able to do more than that, and I really think this is a valuable thing for scientific computing. So I want to go back to the question that I keep asking, which is there anything special about this? And the thing that I would argue is that there is a domain-specific task and the domain and task-specific UI for users. There are domain-specific querying and analysis frameworks, but the bulk of the hard technical problem is a problem that is not domain-specific and we should be working on collectively as a community. People who are interested in computation, who are interested in giving scientists these tools in order to build this domain, in order to be able to do their domain science, is what we really want to be doing is building these small thin domain-specific abstraction layers on top of these general computational workflows. So look, I'm sure everybody in here has a definition of a workflow that they like. I'm going to provide a definition of a workflow that makes sense to me in terms of what I'm doing. I'm not claiming this is the definition of workflows. I'm claiming this is the definition of workflows that I work with when I'm thinking about what I want to build for users. And to me, a workflow is an abstract computational pattern wrapped up in a nice, easy to use framework that allows scientists to focus on science. That's the way I think of workflows. That's the way we think of workflows in the OpenCosmo project. It is one aspect of workflows. It's not the whole thing, but it's really the direction we're going. And something that I believe that is really critical to the future of computational science, especially as computational science, more and more people are doing computational science in sort of the modern era. So I want to revisit my question again from the beginning. So I asked the question is, what do we do about this? We have this user who has one technical requirement, which is I want to train a model in an hour, who knows very little about HPC, who knows very little about any of the details of how you actually do this. What should we do about it? Well, the thing I did in the moment, and I think is a very reasonable thing to do, and I think what a lot of people would advocate, again, very reasonably, is we do education, right? We say, well, I said, well, this is what MPI is, and I can point you to, there's complications of running like containers with MPI, but here I can point you to the facility has documentation that you can point to, and here's the support line, and you can send them an email, and they'll help you out and all these things. And that's what I did in the moment because it's the only option at that time. I would argue a better solution is managed services for users, where a user can come in and say, this is what I need to do, and they don't have to think about the details of how that actually gets done. And these are hard to build, right? Building these at scale and actually doing them across many, many facilities is actually really challenging. But it's a technical challenge that I believe is very achievable, and it's what we're doing in the OpenCosmo project, right? It's about recognizing that doing really, really good, excellent science is a skill that you can spend a lifetime getting good at. And doing really, really good computational work and building really good tooling to do science at scale is also a skill that you can spend a lifetime getting good at. And we believe that the future, that at least what we're doing, the right thing to do is to find people who are good at both things and get them to talk to each other, and let the scientists focus on their science need and let the computational people focus on building the computational things that enables the science. I am an astrophysicist, but what I conceive of myself mostly as an engineer who speaks the language of astrophysics, understands the needs of astrophysicists, and can translate those into recognize the core computational patterns and do that. And that's what we believe, that's what we do in the OpenCosmo project. It's a real working, functional, production level project. We have users using it regularly who are actually doing real science. We also have agentic people. We also are starting to do agentic stuff through this. We have some people really exploring that. And so, I heard a mention of wanting to talk about agentic workflows, and I can certainly find someone who would be very interested in talking about agentic workflows on our platform if that would be interesting. So this is what we're about in OpenCosmo. Like I said, I like to make a bit broader point, and that's the broader point, which is that I think workflows cover a lot of computational ground. But for us, workflows are about making doing science easier for scientists. And in that sense, a workflow is not a user-facing abstraction for the scientist. It's a tool for us to actually build something that allows them to do really amazing work and keeps everybody happy. So with that, I just want to do some thank yous. So this is the core team. The top row is like the core technical team. Bottom row is admin and support team. So Michael Wellmont, I'm kind of the second person on this project. Michael was the first, and he really laid a lot of the groundwork for how this all works. Patricia Larson as well. Will Hicks, fellow postdoc, who was hired to work on this with me. Monpreet is our front end guru, who's really doing amazing work to build that thing. And then, of course, our group leader, Katrin Heitman, and Salman Habib, and then our folks at ALCF who have really worked hard with us to get this working, Benoit and Tom Urim. So I hope that I presented not just an interesting technical thing that we're building, but also some ideas about how that thing relates to the larger scale computational challenges that we face. And if you disagree or have comments, I'd absolutely love to hear about it, because the best thing that we can do is have a conversation about it. So thank you all for your time and attention. I will take questions and comments.